Ever wonder how the Uber Eats app feels like it's literally reading your mind? You open it up and boom, it suggests exactly what you're craving. Well, welcome to this explainer. Today, we're going to peek under the hood and uncover the absolute massive amount of data synthesis making that happen. We're looking at how they totally transform their home feed into a highly dynamic, generative recommendation engine. It's a complete architectural overhaul, touching everything from how they track your behavioral sequences to super fast, real-time machine learning infrastructure.
So here's our game plan for this evolutionary journey. We'll quickly break down the initial home feed challenge, look at the addition of behavioral sequences, the crucial switch to real-time, the generative leap they took, how they optimize the actual hardware, and finally, what the future of discovery looks like. Let's get into it. Starting right off with part 1, the home feed challenge, and why they absolutely had to move beyond just static statistics. Look, the Uber Eats home feed is their primary discovery engine, and its main job is to reduce your cognitive load. Basically, it wants to make choosing your dinner as brainless as possible. But the older architecture, which was known as the deep CVR model, had a huge limitation. It had to process literally billions of signals, but it relied way too heavily on aggregate static statistics. It's kind of like looking at a summary of a movie instead of actually watching it scene by scene. It totally missed the chronological nuance of your journey. Sure, it knew you like pizza in general, but it didn't know you just spent 5 minutes scrolling through sushi before landing back on the homepage. To solve that missing chronological piece, we move to part 2, adding behavioral sequences to truly understand the element of time. To capture how your intent evolves over a session, the engineering team introduced this incredibly powerful hybrid model. Traditional architectures, those deep learning recommendation models or DLRMs, they mostly just looked at your steady-state preferences. But this new hybrid architecture, it brings in a transformer-based sequence encoder. It actually uses multi-head self-attention layers to analyze the exact chronological sequence of your actions. It tracks your clicks, your orders, exactly as they happen, so it can pick up on those subtle little shifts in what you're hunting for right then and there.
And to really squeeze the most out of that sequence data, they use a technique called target-aware sequence modeling. Instead of just looking at your search history in a vacuum, the system actually appends the specific target store it's evaluating directly to your behavioral sequence. This lets the transformer compute the direct mathematical relationship between your past behavior and that one specific candidate merchant. So it's not just asking, what does this user generally want? It's asking, based on their last 10 clicks, exactly how likely are they to order from this specific burger joint?
But sequence modeling by itself isn't a silver bullet, which brings us to part 3, switching to real-time, and the absolute need for immediate context.
You see, even with that incredible sequence tracking, the team was facing another massive hurdle. Their old batch process features had a 24-hour data lag. To fix this, they built what they call the next personalization platform. Imagine this seamless pipeline. You do something on the app. Instantly, the user context system logs it. Right away, Java-based feature extractors compute the new features on the fly, and the online feature store updates. The system literally learns what you want while you're still deciding what you want. This real-time switch is just a massive upgrade. By moving from legacy batch features to this near real-time user context system, they slashed the data lag from a full 24 hours down to mere seconds. And crucially, they used Apache Spark to guarantee identical online-offline training parity, meaning the data the model trains on offline perfectly matches what it sees live in production, which prevents any weird skew in its logic.
Now, where this really shines is with cold start users. These are brand new folks with zero history on the platform. In the old days, they'd just get super generic recommendations for their first 24 hours. But now, the model instantly adapts to their very first clicks, learning their vibe within session 1. It's a total game changer for getting new users to actually stick around and find value right away. To process all this real-time data even faster, we jump to part 4, the generative leap, shifting to a fully transformer-centered architecture.
Okay, so while the hybrid approach was a huge step forward, evaluating every single restaurant one by one was dragging the system down. The fix was fully embracing GenRec, or a generative recommender. They moved away from having separated parallel paths for sequence and non-sequence data. Instead, they made the transformer the absolute core, the primary trunk of the whole recommendation model, enriching all those features together in one place. This architectural shift allowed an amazing leap from point-wise to list-wise parallelism.
With Pointwise, the model predicts a score for one single user-to-store pair at a time. It's incredibly tedious. But listwise parallelism, that lets the model take an array of candidate stores and generate scores for the entire list in a single forward pass. It's way more efficient because the AI is basically scanning the whole page of merchants at once rather than staring at them item by item.
Of course, running a model that heavy requires serious power. That brings us to part 5, optimizing the machine by overhauling the hardware. To run this beast without crushing the app's latency, the underlying machine learning infrastructure needed some major fine-tuning. They migrated over to PyTorch v2 for better flexibility and threw in multi-hash embeddings to speed up training. But the real win for you and me? They transitioned to an offline ONX to TensorRT conversion. This completely wiped out those massive 10 to 60-second startup delays, giving us near-zero cold start latency. You open the app, and it is instantly ready. And they pulled off this speed through a really clever division of labor. This CPU/GPU disaggregation is vital. By forcing all the heavy feature preprocessing onto dedicated CPUs, they freed up the GPUs to focus 100% on high-speed model inference. Splitting the workload like this drove double-digit throughput improvements, basically giving them the computing headroom they desperately needed to run these generative models smoothly. Which finally brings us to part 6, the future of discovery. Let's look at how they're pushing the boundaries even further. With this incredibly fast, real-time generative foundation completely locked in, where does a discovery engine like this even go next? Well, the engineering team isn't resting on their laurels.
They've mapped out 3 super ambitious goals. First up, account life sequence learning, meaning looking way beyond your current session to analyze habits you formed over months or even years. Second, 2D whole-page personalization. Instead of just ranking a 1D list, they want to optimize the entire 2D layout of your screen, the carousels, the visual flow, the whole shebang, all at once. And third, deeply integrating physical, real-world constraints.
As this quote from the team highlights, optimizing for a physical delivery radius while encouraging digital discovery is just an incredibly unique challenge. It's not just about what you want to eat, it's about what can actually be cooked and driven to your specific address while the food is still hot. It bridges the digital and the physical in a really cool way.
Hopefully this explainer gave you a solid look at the incredibly dynamic tech running quietly behind the scenes just to bring your next meal to your door. From static batches to real-time generative leaps, the progress is just wild. As these algorithms get even smarter, mapping out entire lifetimes of eating habits and predicting whole 2D interfaces, what physical constraint do you think AI is going to conquer next? Think about that for a bit, and we'll catch you in the next explainer.